In multi-attribute utility theory, there are two pieces of analytic process. One assigns weights to the various measures or objectives, and that is used to reflect the importance of each measure or objective. And then there's a second part, which is to convert the data, the raw data, into a scale between 0 and 1, and that's called the single utility function. The default assumption for the form of the single utility function is that it is linear. In this tutorial, we will explore the options available in logical decisions to make the single utility function a nonlinear function. We'll look at it for a continuous measure. We'll present two different approaches. One will be an informal approach, and the second one will be a more formal process called mid-level splitting. We'll also address the issue of a single utility function that's nonlinear for a label measure. In general, the default assumption is a reasonable assumption that it is linear with regard to continuous measures. However, for label measures, you should generally be careful and seriously consider assigning a nonlinear SUF. The example we will use to illustrate nonlinear single utility functions involves 3 light bulbs, a halogen, incandescent, and fluorescent. In this table is the goals hierarchy and the measures. One goal is to maximize quality, and quality of light is measured by the amount of light and the type of light. The type of light refers to halogen, incandescent, fluorescent, and we will illustrate how to introduce a nonlinear function for this label measure. The second goal is minimize costs. It has 2 pieces, purchase and operating. Operating is a standard continuous function, but again we will explore how to make it a nonlinear function and rescale it between 0 and 1. In the next 2 slides, we'll show the information as it relates to the lighting example as it appears in logical decisions. This is the standard goals hierarchy. You'll see maximize quality is given a little more than 50% of the weight, and minimize cost is 48% of the weight. The maximize quality, more weight is given to type than to amount, and within minimize cost, operating cost is significantly more important than purchase cost. Here is the standard data matrix that appears in logical decisions. The first column is the amount of light. The second column represents the cost associated with operating. Notice it's in pink. That represents the fact that this data is actually a probability distribution, and the values you see in each cell is the expected value for the operating cost. The reason why it's uncertain is you never can be sure how many hours over the course of a year you will keep this bulb on. Purchase information is on the next column, and we have the label measure type, fluorescent, halogen, and incandescent. So here are the results when we assume that each SUF is linear according to the default assumption. The halogen is almost 0.62, significantly better than the incandescent, which is 0.51. And the fluorescent is a distant third, 0.42. The strengths of the halogen, it has strength with regard to type of light, and notice that the green bar is twice what the incandescent green bar is, and it also has strength with regard to the amount of light. On the other end of the spectrum, it's poor with regard to operating cost, and in our example we're going to make operating cost nonlinear, and we're also going to make the type of light nonlinear. The results matrix for the same example that comes out of logical decisions is presented here. And the thing that will be most interesting down the road is we will be looking at nonlinearity with regard to operating measure. And you see the halogen bulb is 0.213 on the operating measure, incandescent is slightly better, 0.324, and the fluorescent is 0.920. These numbers between 0 and 1 will change when we introduce a nonlinear function. The other measure that we will be considering is type measure. The measure says that for halogen it's a 1, for incandescent it's a 0.5, and fluorescent it's 0. Given that there are 3 potential values for the type measure, the default assumption is the best is 1, the worst is 0, and the middle one is 0.5. In this section we'll be discussing how to create a single measure utility function, and we're focusing on an informal method which says, let me consider the shape being either convex or concave or something like an S-shaped. There's no right or wrong answer. for what a SUF is. It depends upon context and personal preferences. And one of the things we'll be talking about, but without actually giving a good example, is that when you use this informal method, you're using it to see whether or not linearity has any impact. So you suggest a shape that you think is consistent with your understanding of this particular measure and the attitude towards this measure, and then you would check whether or not the rank ordering of the alternatives was in any way influenced by the nonlinearity of the SUF. Definitely the scores will change, but that may not at all change the ranking, and in that case you may just stick with a linear function. At this point, we're just going to walk you through the basic steps where in logical decisions this information is. Our example is we're focusing on the operating costs, and we're going to introduce a nonlinear single utility function for this cost function. Now, this cost function is of the type that as you move to the right, as the value gets larger, the utility gets smaller, and if you move to the left, as the value gets smaller, the utility gets larger. So first, we just click on operating and select that. Now, what we want to do is assess the SUF, and that in this case means assess the common units. So we click on assess. Later on we'll show an alternative to clicking on assess, but we'll click on assess and we'll see that the menu that comes up is that we're interested in is common units. Previously we were interested in assessing the weights. This is the menu that will appear. So under measure you want to make sure you're looking at the right measure, in our case operating cost. And the only assessment method we're going to use is SUF, the simple utility function. There are other more complex approaches. So you click on, make sure that SUF is highlighted, and we click on assess. When you click on that, the first screen that will appear is the operating cost SUF, which the default assumption is that it's linear. You'll notice in the middle there's a green square. That green square is positioned at the midpoint of both the cost function and the utility function. So the midpoint in this case is $175, and the utility of $175 is 0.5. We're going to be changing that to create nonlinear functions. In this example, we're going to look at a convex function. Now, this particular picture shows a convex function, whereas the measure increases, the objective function increases. Our example was actually a complementary picture, but it's still convex. When something is convex, that means moving a small amount from the zero utility value, moving along the measure a small amount does not dramatically increase the utility. Until you start moving significantly far from the worst measure, only then does the curve get to be steeper and steeper. And its steepest point is as you get closer and closer to the best measure level, and the utility function becomes 1. To give an example, if you're in an NBA draft and the difference between moving from the 24th choice to the 23rd choice might be small compared to moving from the second best choice to the first choice in the NBA round. That would be a convex function that would be consistent with this type of utility function. But again, in that case, the higher number is the worst case scenario and the lower number is the best, as we'll see in our operating cost example. And here's the curve that we're going to be working off of, and all we're going to do is change its shape to be of a convex form. And the way we're going to do that is we're going to drag the button to make a convex functional form. If we click and drag that button, as we move it, it will change both the utility score and the level. In this particular example, we stop at a point that has a utility score of about 0.26, and the level is $122. That means, in this example, improving from 300, reducing the cost from 300 to 122 does not get you that much increased utility score. It only increases it from 0 to 0.26. And there's a very steep improvement when I go from $122 down to $50 in cost. In this example, we're going to look at a concave function. And the concave function means small improvements from the worst value makes things better. And less value is added as you approach the most preferred level. So We'll see that in our example of operating costs. Again, we start with the default assumption that's a linear utility function for operating costs. And now we're going to move the box in such a way that we produce a concave function. In this particular example, what we're saying is $300 is a zero utility, but if we can get it even slightly better, it has a dramatic impact on our utility. So in this case, just improving it from $300 to $211 or $212, which is an $80 improvement, we increase the utility to 0.78. We're very sensitive to extreme costs. We want to get it closer and closer to 200, but as we get beyond, let's say, 200, the improvements, the value of improving from 200 to, let's say, down to 50 will be minimal. Okay, here's our third example, which is an S-shaped curve. Small improvements from the least preferred value don't get us very much. Similarly, small improvements as you get closer and closer to the most preferred value, that the slope of that line is also flat. The steepest part of the curve is in the mid-range. That's where we're most sensitive to changes in that measure level. We'll see that example, how you do that with the operating cost. Here we need one extra step because we want to have an S-shaped curve. That means we need to look at each half of the curve separately. In order to do that, we need to click on the button Split Range. After clicking on Split Range, you're going to have to click on one part of the graph. In this case, we clicked on the upper left-hand half of the linear function, and that point happens to be 0.75 and 112.5. That's for the linear function. We're going to move that to create a different shape. After clicking on the green box, we're going to move in such a way to create a concave function in the upper left-hand part of the curve. In this example, we're just picking arbitrary numbers to illustrate how you can create an S-shaped curve. In this example, as I move that green box to a point where the utility function is 0.89 and the value is 137. That means when you go from $50, which is at a utility score of 1, up to $137, the utility has dropped slightly, but not a lot. It's gone from 1 to 0.89. Now you have to select the other section to create the other part of the S-shaped curve. So after clicking the lower half of the original linear function, you can drag that box and create the convex part of the curve. So in this section of the graph, we created a convex function, and we move that midpoint. Now it's at the value of 199, and its utility is 0.14. So recall where we were. We have 0.89 at $137 value and 0.14 at $198. So the middle section of this graph, ranging from 137 to 198, 199, covers 75% of the utility function. That's the steepest part of the curve. Once you get either close to the best score around 50, every additional dollar that you save doesn't add much. And similarly, when you approach 300, every additional dollar that it costs you does not decrease the utility. It's only in the middle range where there's a steep impact of every dollar. In this example, what we were doing was somewhat arbitrary. It was just to illustrate how you create different shapes. You would use this technique in an informal way. If you thought the curve was either convex, concave, or S-shaped, you produce something that you felt was reasonable, and then you'd rerun the model to see what the results and if it changed anything. If it did change the rank ordering, then you would go through a formal process to ensure that you had an accurate reflection of what the utility curve should be that represents your own value system. And we will be doing a more formal process in the next few slides. So we're once again going to introduce a nonlinear utility function for the operating cost. Since we had already input some information in various curves, we need to reset it to the default assumption of linearity before we begin using mid-level splitting to create an appropriate curve. Logical decisions will ask you to double check whether or not you really do want to reset the SUF for operating costs, and in this case you click yes. Okay, so this is a table that would reflect what we may have found after we've done an interview. The utility of 1 assigned to $50, the utility of 0 to 300. In this particular case, that's a range of 250. 175 would have been the midpoint. The question is, where do I really believe the midpoint is in the utility function? Is it closer to the 50 or is it closer to 300? In this particular case, the feeling was that if you went from 300 to 230, you would have a dramatic impact and the utility score would rise from 0 to 0.5, even though you only made a $70 improvement. The next step is we look at two other midpoints, and that's why it's called mid-level splitting. We look at the 25th percentile and the 75th percentile. And between 230 and 300, the midpoint would be 265, but continuing the shape of the curve that we had before, we say that going from 0 to 270 already improves the utility score from 0 to 0.25. And similarly, maintaining the same shape, from 230 to 50, you improve the utility score from 0.5 to 1, but you get most of that benefit by just going from 230 to 160, which is a drop of 70, and then the continuing drop from 160 to 50, which is a drop in cost of 110, only generates an additional 0.25. This is a formal process that one would learn how to do this interview. We're going to just illustrate how you would then input this information into logical decisions in the next series of slides. We go through the standard steps. We click on operating cost, and we say we want to assess, and we want to assess the SUF. When you clicked on assess, the default appears, and recall that the green box in the middle is at the point 175, a value, and a utility score of 0.5. What we want to do is simply change the 175 based on our table of data on the previous slide to 230. All we're going to do is input 230 in that box and hit enter. After hitting enter on the previous slide, the graph changes, and this is what the graph would look like. As we mentioned, this is a concave function. As you move from 300 to a lower cost, you have a steep curve, which becomes flatter as you get closer and closer to $50. But we'll fill in points in between as well. Next thing we do, and this is called the mid-level splitting, you simply click on the split range button, which will begin allowing you to input the 0.25 utility score value and the 0.75 utility score value. When you click on the upper left-hand part of the curve, what it does is it changes it from a smooth curve to a piecewise linear curve, and you see in the upper left-hand corner now a green box. That green box now has a utility value of 0.75, and because it assumes that section is now linear, it specifies the value to be $140. Based on the table of values we have, we want to input 160 instead of the 140, and when we hit enter, it will change the shape of the curve in that section. Now we want to deal with the lower half of the curve, which is still piecewise linear, and the current value has 0.25. The value is $265. So we're going to click on that section, and then we're going to assign an appropriate value to a utility of 0.25. We go into the box where the level value is, and we replace 265 with 270, and we hit enter, and it should reshape the curve, and now we have our nonlinear curve that's been smoothed by logical decisions. In this section of the tutorial, we will be dealing with a label measure, and we want to introduce a nonlinear utility function. And in general, I would encourage serious consideration of nonlinearity whenever you have a label measure, rather than using the default, whereas it may not be as critical when you have a natural measure that has costs or profits associated with it or any other natural measure. In our example, we have three types of bulbs. We have a halogen bulb, an incandescent bulb, and a fluorescent bulb. And in terms of the light they produce, that's what we're looking at. And in our opinion, incandescent is pretty close to halogen in terms of its ability to produce a true color, and fluorescent is much worse. So instead of having the default assumption of 1 for halogen, 0.5 for incandescent, 0 for fluorescent, we want to assign a 0.75 value to the incandescent bulb, and that's what we'll show how that's done in logical decisions. So this time we're focusing on the measure called type, and instead of using the word assess to assign a nonlinear function, we're going to click on that icon that shows a nonlinear curve to introduce a nonlinear utility function for the type of light bulb. When you click on the icon and it asks you to input an assessment, the software knows that this is a label measure, so it doesn't even offer you the opportunity of SUF, and the method we're going to use is direct assessment. After clicking on assess, this is the screen that will appear. You'll see the three values, and all we're going to do is replace the 0.5 value with 0.75 and click enter to finalize the direct assessment. After inputting that information, we click done and we're ready to go back and see if it had any impact on the overall rankings of introducing two nonlinear functions, one for operating cost and one for the nature of the light bulb. With the nonlinear utility functions for type of light and for operating cost, the rank ordering doesn't change, but the values have changed significantly. Halogen has gone up from approximately 0.62 to almost 0.69. That increase is because the cost that it incurs with a nonlinear function is not as bad as it was before, and that's what increases it. But with incandescent, the impact is even more dramatic. It benefits from the nonlinear curve in operating costs. But remember, we've also said the incandescent bulb as a type of light is no longer 0.5 in the previous example, but now we've set it as 0.75. So now incandescent is a close second to halogen, whereas before it was the gap between the first and second was much larger. And we'll see in the next slide where those changes occurred. So here are the two matrix results for the nonlinear and the linear assumptions about utility functions. Recall that in the type measure, you'll see next to incandescent in the original matrix in the bottom was 0.5, now it's 0.75, and the biggest difference is in the operating measure. The fluorescent used to be 0.92 because of nonlinearity. It's gotten slightly better. It's 0.955. The incandescent has a dramatic improvement because of the nonlinear operating cost. It went from 0.336 to almost 0.54. And there's also a significant improvement in the halogen cost utility score from 0.22 to 0.395. As a result, if you look at the numbers in the first column, which correspond to the length of the bars, under the new nonlinear utility scales, halogen is 0.687 versus incandescent is 0.66. When they're that close, essentially they're equivalent. Yes, you can go with the best alternative, but if, for example, I already had incandescent lighting, and now I was trying to decide whether to replace it with halogen, given how close they were, I wouldn't bother.